Hey everyone, my name is Bo. I'm here to talk today about interoperability and the journey from messaging to proofs. Thanks for coming this afternoon to listen to this talk. So I want to frame the conversation here with a little bit of a story. So I want to start with the story and I want to end with the story. So imagine a mysterious portal appears, we walk inside, and on the other side, we arrive in 241 BC China. In front of us, we can see the Fei army forming and assembling. And we watch them set out to battle. The general, Shen, in this case, is leading his army against their neighboring countries. The battle itself is fierce and chaotic. The Fei army ends up getting moved around all over the place and is losing the battle. And they need a way to reorganize. The Shen general is faced with a choice. Either he commissions a few horsemen to send a few messages out to notify the troops, or he sets off a smoke signal to notify the troops on what to do. We'll find out what the right answer is at the end of the presentation. So a little bit about myself. My personal background is in database engineering. I worked at a few different startups before founding Polymer. So the Ethereum ecosystem today is expanding rapidly. We're seeing tremendous growth in the number of rollups. Unfortunately, for the long tail of rollups, connectivity is a major issue. We estimate this problem to be only less than 10% of rollups today are densely connected. And this problem is getting worse over time. If we look at the historical timeline of blockchain, starting from Bitcoin, Ethereum, DeFi sparked an era of L1 expansion for a period of time. Although a few rollups launched sooner than 2022, in 2022 we had the launch of the OP Stack, Arbitrum Nitro, and rollup frameworks that ushered in an era of rapid rollup expansion. Soon we'll see the advance of new rollups that are high performance like Mega ETH, Rise, and Soon, and so on. Additionally, during this period of time, you had a lot of different interoperability protocols starting with IBC, Wormhole, Axelar, Layer 0, Hyperlane, and now Polymer launch to solve this problem. Many of these protocols have not been able to keep up with the expansion in the number of rollups. I think Hyperlane does the best job, but still with an inefficient interoperability model. So we can all agree that efficiently scalable interoperability is the key to Ethereum's success, given this rapid expansion of rollups and the rollup roadmap itself. Well, messaging works and is the interoperability mode that's taken by interoperability protocols today. Messaging roughly looks like this. You have an app gateway on the source, you have an app gateway on the destination, an application message is routed through a gateway. Usually you have like a gas oracle component, an off-chain relayer, and messages get pushed through the system. Messages in this model are explicitly sent from origin to destination. This model is generally opinionated on communication pattern, meaning it's generally point-to-point. There's a lot of gas consumption, both on the source and destination. There's increased complexity, latency, and less flexibility overall. So I want to pose a question of, is messaging required for interoperability? With chains being verifiable, we believe that sending a message is unnecessary. With verifiable data, instead of sending a message, we can instead just generate a proof that something happened on chain, whether it's a proof via an event, whether it's a proof via the app state, we should be able to prove things on chain. Polymer is working on a proof-based interoperability system that obviates the need for messaging. Proofs provide a simpler and more efficient solution. The mechanics of it are similar to native interoperability solutions such as superchain native interop. Unlike messaging, proofs are fetched on demand, and the application only needs to integrate with a prover contract on the destination chain for verifying these proofs. This in turn has minimal overhead when compared to messaging. So if we scroll back, we can see that all of the intermediary middleware gets removed for just a proof fetch from the destination. So what are some advantages of proof-based interoperability? Proofs offer simpler user experience. Instead of sending a message, the developer can fetch a proof and then use that proof anywhere on any chain. It's a simpler integration. The application builder doesn't need to integrate an app gateway contract. It only needs to integrate a prover contract on the destination. And there's a simple messaging format. The application either just emits an event or reads a portion of its state. Proofs are also easier to maintain at scale. With messaging, you have to manage the routes between chains. And in the diagram on the screen, we can see that as the number of chains grows, the complexity of managing these routes grows as well. We also have to deal with gas oracle updates. Many protocols maintain an on-chain gas oracle that estimates gas for connected chains on-chain, and this would have the same complexity in terms of managing. Proofs scale a little bit more efficiently. Instead of scaling a bunch of routes across these different chains, you can slap a single API in front that can talk to all these chains and request proofs, event proofs or storage proofs. And the topology of this setup is far simpler. Proofs also give apps more control. Proofs allow apps to choose between broadcast or point-to-point messaging mechanics, and gives apps more control over the guarantees made by the system itself. The app can now determine how fast to go between chain to chain. It doesn't have to wait for the messaging system to determine if the gas price or if a route is profitable for them or not. An app can decide whether or not guaranteed delivery is a desired property. And the app is also allowed to bypass censorship, meaning that the app can directly force proofs through the L1 native bridge. Proofs are also more efficient. Messaging is a sum of send, receive, and verification costs. The estimated gas paid to the system is a sum of receive and verification. With proofs, the only cost or overhead is the verification itself. So what are some examples of proof-based interoperability? We have storage proofs, which is used in RIP 7755 by Base, or Arbitrum's cross-chain broadcaster standard. With storage proofs, what we're doing is we're proving a key value pair in a rollup, and then proving that rollup state on the layer 1 and the layer 1 state that's derived into the connected rollup on rollup B. So if we look at the flow, it's the key value pair to rollup A state, to L1 state, to rollup B state. Then rollup B can fetch a storage proof proving this entire chain of states all the way into its own state. While this works, storage proofs can be quite slow as they go over the rollup native bridges themselves. For example, in the diagram here, we can see that to generate the storage proof for the first leg, it takes 2 seconds for rollup A to produce a block, 7 days for it to settle, and roughly 12 to 16 minutes for the L1 state to be derived into the rollup B state. Overall, this process takes a week or longer. Additionally, these proofs are expensive. The size of this proof can be over 16 kilobytes. And the gas cost, or the execution gas cost, can be over 2 million gas. Polymer takes a different approach. We take the approach of using event proofs instead of storage proofs. This means that the Polymer rollup is responsible for ingesting the block headers of all connected rollups, from which we can prove events against the header itself in the receipts route. In this model, it takes 2 seconds for rollup A to generate a block header, and another 2 seconds for the Polymer rollup to verify a sequencer pre-confirmation from the connected rollup. Roughly about 3 to 5 seconds to generate an event proof over Polymer. These proofs are also much cheaper. They're less than a kilobyte in size and cost less than 60,000 gas to verify, in comparison to over 16 kilobytes in proof size and over 2 million gas to verify. Now, what does Polymer look like in production? I pulled this example from an existing messaging protocol to compare what the costs look like live between two different rollups. In one example that we looked at, the latency of sending a message from chain A to chain B was roughly 56 seconds in an arbitrary messaging protocol. In comparison to Polymer, the latency of fetching a proof and proving it on the connected chain is only 5 seconds. This makes proofs in this one example 11 times faster than messaging. What about the costs? When we looked at the dollar value cost of a message sent between rollups, we could see that in the anecdotal example that we pulled, a single message cost almost $3. This includes the send costs, receive costs, and verification costs, which are bundled in the estimated gas paid to the protocol. In comparison, Polymer proofs cost roughly 15 cents. This results in a 95% cost savings compared to messaging. And when we compare it to a system that's communicating over rollups that are using Alt-DA, the costs are even cheaper. The proofs can cost a cent or less to verify, and this results in over 99% savings. We have many partners building with proofs on mainnet today: Eco, OpenFort, Superform, Everclear, Kalani, and more. Low latency cross-chain proofs are only part of the problem, part of the solution to the problem of interoperability. Like they say, teamwork makes the dream work, and there's many great teams contributing to trying to solve this problem. We have Arbitrum, Optimism, Espresso, Polygon, Across, and many others. Okay, so now back to our friends in 240 BC China, because you're probably wondering why this story and how this story is connected to the problem here. The analogy that I want to make is proofs are similar to sending messengers on horseback. I'm a general. I want to communicate with different parts of my army in real time. I can choose to send a bunch of messengers on horseback to communicate to each of my units, or I can set off a colored smoke signal to indicate to the army on how they should reorganize and what they should do. The recommended choice here is to just send off a smoke signal. I can communicate to the entire army at once. I don't need the overhead of a bunch of men on horseback. The latency is just faster, the overhead is cheaper, and I'm able to do this at scale across a very large battle, a very large army. So the Fei army sends off a smoke signal to notify its troops to reorganize. Their army was able to regroup, and the Fei army was victorious. If you're interested in building with proofs, or cross-chain proofs, if you want to build a cross-chain apps, whether it's an intent-based application or just a multi-chain DeFi application, please reach out to me. We have a website that's listed here, and you can find me on Twitter at 0xbodu. Thank you.